absolutely. I'm going to share my screen. I think. Let's see. Can you see this slide okay?
Yep.
All right, fantastic. Thank you so much, Nicole. So yes, I'm Beth Ament. I lead our Georgia community and also our Tennessee community with the U.S. Green Building Council. And I'm just taking a couple of minutes to tell you a little bit more about USGBC and how you can get involved. So just a quick intro into the background. We were founded in 1993. We're committed to a prosperous and sustainable future through cost-efficient and energy-saving green buildings. When USGBC was founded, we started with this mission, which is to transform the places where we live, learn, work, and play within a generation. And we do this through LEED certifications and professional credentialing. So for more than 25 years, actually this year it's 28 years, our member companies and our green building communities have come together to make our planet stronger, greener, and more sustainable. So as I mentioned, USGBC works towards its mission through its LEED Green Building Certification Program, which I'm sure a lot of you are familiar with. In addition to that, we have robust educational offerings, a nationwide network of chapters and affiliates, the annual Green Build International Conference and Expo. And then we also do advocacy and support of public policy that encourages and enables green buildings and communities to prosper. So our membership, who we're made up of, it's super diverse. As you can see here on the screen, it's everything from real estate leaders to governments to contractors and even more. Just to give you a little bit of heads up of what's going on in Tennessee, we currently have 81 individual members. And then we also have organizational membership. So it's a national membership where your company can get involved. We have 95 of those currently in Tennessee. As far as LEED certified projects, Tennessee is very robust. We have 486 certified projects and 411 registered projects. So I just want to end on encouraging you to join us for one of our upcoming programs that we have that is hosted by the USGBC Tennessee community. You do not have to be a member to join us, but if you are interested in learning more about membership, you can contact me. I'll pop my email into the chat after I'm done speaking. But you can see we've got, in August, we have a showcase, LEED project showcase focused on public safety. We've got our Women in Green program, which we do that with Tennessee Women in Green. So TWIG, if you're familiar with that organization. We actually have nominations open right now for the Leadership Award for that. So feel free to nominate someone there. And then we have our Impact Leadership Awards in November. So thank you guys so much for your attention and your energy. I really look forward to the rest of the program. And I will stop here and stop sharing.
Thanks, Beth. So I think the rest of the hour we'll hear from Anthony. Anthony is so kind to speak to us and educate us. So Anthony is the principal at Priopta, a leading firm with deep expertise in life cycle assessment for buildings. Priopta empowers architects and engineers with the data and knowledge they need to reduce embodied carbon. Anthony is also the founder of CLF Vancouver, the first local hub of the Carbon Leadership Forum, which organizes local events that empower industry professionals to radically reduce embodied carbon from buildings and infrastructure. Since 2019, CLF Vancouver has inspired over 25 other cities to start CLF local hubs. He now also serves as a CLF Regional Hub Director, supporting local hubs across Western North America and Asia Pacific. He is a professional engineer with a master's in Industrial Ecology from NTNU, which is a leading LCA research group in Norway. Anthony distills the latest developments and knowledge on embodied carbon through his presentations to leading design firms and at industry conferences. So with that, Anthony, if you want to go ahead and share your screen.
Thanks, Nicole. And yeah, it's great to see your guys' efforts to launch a CLF National. I think this is your first webinar or something? Or no, you've already had a first event, right?
Yeah, we had a meet and greet. This is our first educational event.
Awesome. Great.
So thanks for
It's good to see
supporting
that.
us.
Yeah, no, totally. It's great to see that take off. All right. Let me share my screen. Okay. And all right. Well, hi, everyone. Thanks for joining this presentation. So today I'm going to be talking about embodied carbon, which I oftentimes refer to as the blind spot of the buildings industry. Okay, so here's a brief outline of the presentation. First, I'm going to go over what is embodied carbon and why does it matter. Then I'll dig into how does embodied carbon compare with operational carbon, which is the emissions associated with energy, like operating our buildings, and a domain that we're more familiar with. So how do these two metrics compare? Then I'll dig a bit deeper into some of the policies and standards that are addressing embodied carbon. I'll give an overview of how do you calculate embodied carbon, which is using life cycle assessment software tools. So I'll give an overview of some of the different tools out there that are commonly used in industry and how they compare. And finally, I'll wrap up with a section talking through about design strategies for reducing embodied carbon. So I'm going to go through individual key material categories like concrete, steel, wood, aluminum, glass, insulation, refrigerants, mechanical, electrical, plumbing systems, and interiors. And then we'll have some time for Q&A at the end. All right, so first off, why does embodied carbon matter? Well, when we're talking about embodied carbon, we're referring to the emissions associated with construction materials. So think of all the materials that go into a building, all the concrete, steel, wood, glass. There's carbon emissions associated with that throughout all the life cycle stages. So everything from extracting those resources, like the mining and the harvesting of the timber and et cetera, to the transportation of those materials, to the manufacturing and processing of those materials, all the way to construction, operation, and even at end of life. So if you think about the supply chain of all these materials throughout the whole lifespan of the materials and the lifespan of the building, what are the emissions associated with all those pieces? That's what we quantify using life cycle assessments. Now, how significant is embodied carbon globally? If you look at, this is a pie chart showing you the global annual CO2 emissions. And currently, about 28% of global CO2 emissions is attributed to operational carbon. So that's operating all of the buildings on the planet right now, heating, cooling, operation. So that's 28%, and that's obviously a big chunk of the emissions. That's where we have historically had a lot of focus on in the green building sector. However, there's a further 11% slice of the pie, which is attributed to embodied carbon. So that's associated with all the materials and all the new construction taking place each year. That includes major renovations as well. So that's 11%. Another way of slicing this up is looking at just some of the key materials that are used in our buildings. So concrete, steel, and aluminum. Together, they account for almost 23% of global CO2 emissions. Now, obviously, the building sector doesn't use all the concrete and steel and aluminum in the world. These materials are also used in our infrastructure. They're used in, for example, manufacturing cars or other products. But the reason why I'm pointing this out is that as a building sector, we have the opportunity to transform some of these supply chains to create demand for low carbon concrete, low carbon steel, low carbon aluminum, and other materials. And if we make those changes and those changes happen in the supply chain, it doesn't just affect the building sector, it can have a broader impact, towards infrastructure or other categories that use these materials as well. So we can have a big impact with our design decisions. What about the new construction? So if we just look at how much new construction we're projected that's projected to take place between now and 2050, so over the next 30 years, and you just look at that cohort of buildings that gets built between now and 2050, the embodied carbon associated with that building stock accounts for almost half of the total new construction emissions, with the other half being operational carbon emissions. So this is quite significant. Half of the emissions of all the new construction over the next 30 years is coming from embodied carbon, which we have typically actually ignore on projects. We don't even quantify, we don't calculate, we don't try to reduce it. That's particularly important because we're projected to double the current building stock by 2060. So think of all the buildings that currently exist on the planet, all the square footage. We're going to double that in 40 years. And so this diagram shows you a breakdown of how much new construction is projected to take place across each continent or region. So you can see how much is projected to take place in North America. The size of the circle refer to the floor area built, like billions of meters squared of floor area. And the different shades refer to, how much is going to get built by 2030, by 2040, by 2060. And you can see, there's quite a bit of new construction taking place in North America. There's obviously a lot happening in China, and in the later decades, in regions like Africa and India are going to be quite significant as well. So a lot of new buildings. That's equivalent to building an entire New York City every month for the next 40 years. And just let that sink in. Think about like how much floor area there is in all the buildings in New York City. That's all across all 5 boroughs, not just, Manhattan. I think it's something like 5.8 billion square feet. That's how much we're building every month for 40 years. So that's a lot of buildings, that's a lot of materials. Now, how does this map to our climate goals? To hit to limit global warming to 1.5 degrees Celsius, according to the IPCC report, we needed to peak global emissions last year, which we actually did, large part due to the COVID pandemic. And then we need to half global emissions by 2030. And then we need to get to 0 by 2050, and then go negative afterwards. And so you probably heard recently, Biden had announced like a 50% reduction target by 2030. So that's in line with this 1.5 degree scenario target. Hugely ambitious. To actually achieve that rate, that means we need to reduce globally, reduce emissions by 7.6% per year. And I think last year, I think this may be a bit outdated, but I've seen a range of estimates. It was roughly about 7% reduction, 7 or 8% reduction last year. But that's from like halting big sectors of the economy, right? So think about what it actually takes to achieve that year over year to create that level of reduction. All this to say, embodied carbon is a key piece of this puzzle, but there's no way we're going to hit any of these climate targets if we continue to ignore embodied carbon. So let's bring this down to the building level. How does this compare with operational carbon? And the key metric I want to look at is kilogram of CO2 equivalent per meter squared of floor area. Excuse the meter squared. I know that's not the same as the imperial system, but yeah, it's roughly like a tenth of a square foot, or it's roughly 10 square feet to a meter squared. So this is an overview of let's say like a hypothetical building. So let's say the building lasts for 60 years over the whole lifespan. Every year, there's going to be some operational carbon emissions, right? So that's heating and cooling the building. And, during the design phase, we quantify that using energy modeling. And so this is something that we're all very familiar with. This is something that gets done in the design phase. We're trying to, inform decisions to reduce operational carbon emissions. But then there's also the embodied carbon. And embodied carbon, upfront, before the building's even occupied, there's a big pulse of the emissions. Most of the embodied carbon is before the building's occupied, because that's when all the materials gets manufactured, produced, that's where most of the emissions are. But then we also account for things like replacements and maintenance throughout the lifespan of a building. So if any building components, let's say it lasts 15 or 20 years, but the building lasts for 60 years, we account for those replacements. And then finally, end of life. If there's any emissions associated with deconstruction, demolition, landfilling for those materials, we account for that as well. And to do that, we use a life cycle assessment. So you can think of LCA as kind of analogous to energy modeling to analyze both sides of this equation. Now, when we do a life cycle assessment, while most people talk about the carbon emissions or in the embodied carbon, this is actually only one of many environmental impact categories that we quantify. So when we do an LCA, we look at global warming potential, or GWP. That's what we refer to when we say embodied carbon. But then we also look at things like acidification potential, eutrophication potential, smog formation, depletion of non-renewable energy, and ozone depletion. So these are some other environmental impact categories that we look at. Now, I mentioned we quantify this using life cycle assessment. So what do we mean by life cycle? So there's formal definitions for each of these life cycle stages. Broadly speaking, module A, there's module A, B, and C, and D. So A refers to the upfront carbon. So that's all the emissions before the building is occupied. So that includes raw material extraction or supply, transportation, manufacturing. So that's A1 to A3. That's what you sometimes see in environmental product declarations for different material products. And then we also account for transportation to the construction site, and then any emissions associated with the construction and installation process. So that's module A, and this is where most of the emissions for embodied carbon typically comes from. Then we have module B, which is during the use or the operation phase of the building. So any emissions associated with the use of the materials, maintenance, repair, refurbishment, replacements. Typically replacements is where most of the emissions in this module are. And then finally, we have end of life. So at the end of life of the building, the emissions associated with deconstruction and demolition, transportation, waste processing, and disposal, that's all in this stage. And so typically when you look at a life cycle assessment study, the main results are from module A to C. So A to C is the main result. Sometimes you see they report module D, which is benefits and loads beyond the building life cycle. So that's accounting for example, if there's benefits associated with reusing the materials at the end of life or recycling it. As you can imagine, that kind of affects the next material after the building product, right? So like if you recycle the material from your buildings, that recycled content goes to the next product. So how do you account for the benefits of that? So this is typically reported as supplementary information, but the main results are the A to C results. So if you combine that with your energy modeling results, which is operational carbon, that's how you get sort of a whole life carbon or a holistic picture of all the carbon emissions associated with your building. Now, historically, the thinking has been that operational carbon emissions are far more significant than embodied carbon. So maybe it's okay to just ignore the embodied carbon. But what we're seeing is that over time, as we decarbonize our buildings, as we design more energy efficient buildings, and also we decarbonize our electricity sector, and so our electricity grids are lower carbon, the operational carbon emissions drops. And as they drop, the embodied carbon becomes a bigger slice of a smaller pie, so to speak. And the reality is this equation changes drastically from region to region, from city to city, because those parameters can change quite a bit. Even the electricity grid can change quite a bit. So, I'm from Vancouver, Canada, and in British Columbia, in our province, we have fairly low operational carbon emissions. So we already have designed fairly efficient buildings, and we have a very clean electricity sector or electricity grid. And so I won't get into the details of this. This is something that we have that's called the BC Energy Step Code, but I'm just trying to create a frame of reference for the operational carbon emissions and the embodied carbon emissions. Broadly speaking, we actually have measured some of the buildings, like 500 plus buildings for the first time this year. So we have a benchmark report. So let's say a typical multi-unit residential building is around 20 kilograms of CO2 per meter squared per year. So that's to operate the building, heating and cooling it every year, around 20 or 21, offices around 15. However, if you're kind of complying with our BC Energy Step Code, which is where our building code is going towards, as you get higher in the steps, you get more energy efficient. And one of the key things for us is in BC in particular is that if we electrify our buildings, because we have a lot of hydroelectricity, our buildings get very low. They can get down to 1 to 2 kilograms of CO2 per meter square per year. So at that scale, obviously the operational carbon is so low, the embodied carbon can be quite significant. Before I share about the embodied carbon, like the range of emissions that you can expect for embodied carbon, I want to touch on the electricity sector, because this can obviously really affect your operational carbon emissions of your building, especially if you use a lot of electricity in your building. And just to show you that there's big variations, right? So I mentioned in British Columbia, we have a lot of hydroelectricity. So we're around 10 grams of CO2 equivalent per kilowatt hour, which is extremely low. Alberta, our neighboring province, and also where I'm from, has a lot of natural gas and coal in the electricity supply. So that's around 800 grams of CO2 equivalent per kilowatt of electricity. So you can see there's huge differences there. Now to a graph that's more relevant for all of you in the States. So I've actually graphed out, this is based on EPA data, all states in the US, and I ranked them from highest to lowest. So you can see grams of CO2 equivalent per kilowatt of electricity. So you can see the range in emissions all the way down. And then you can see, for example, Vermont, very low, 26 grams of CO2 per kilowatt hour, because they have a lot of renewables. So the blue bar is talking about the electricity grid carbon intensity. The red bars show you how much is generated each year. So you can see, for example, Texas is a big state that they generate the most electricity out of all the states. And so you can see, how significant that is as well. And then the third column shows you the electricity grid mix. So I show a breakdown between coal, which is the black, brown is the natural gas, and then all the lighter colors are the renewables. So you can see, a lot of coal in Wyoming. And so therefore, the electricity grid mix is very high. Whereas in Vermont, lots of renewables, lots of hydro and biomass and et cetera. That brings it quite down. So this is just to calibrate, because this is going to affect your operational carbon emissions quite significantly. Oftentimes when we're talking about operational aspects of the building, we're more focused on the energy metrics, like energy use intensity, kilowatt hour per meter squared. But that obscures what the actual carbon emission impact is. And we're using energy as a proxy for actual greenhouse gas emissions. And when we look at greenhouse gas emissions, we need to actually think about the grid carbon intensity. And then this is just one further graph showing you how it varies between different countries at a national level. So, nationally, the average for US is like around 470. And you can see in Asia and China and whatnot, like it's, close to 1,000, right? So there's a lot of coal electricity there. So you can see how it varies, in different regions, different countries. So, okay, that was a bit of a sidebar. That's talking about the electricity mix. Now I want to get back into the embodied carbon metrics. So we know on the operational side, it can vary quite a bit. On the embodied side, it can also vary quite a bit. So you can see this was a study done by the Carbon Leadership Forum back in 2017. They looked at 1,000 life cycle assessment studies from around the world, and they compiled it. And you can see there's a big spread in the emissions. And it could be below 100 kilograms of CO2 per meter squared, all the way to 1,000, with many of the results in the 200 to 600 range, let's say. Similarly, One-Click LCA, which is one of the software tools, and they've developed their own benchmark as well for different building types like offices and apartments. And they created a letter grade rating system. So for example, if it's below 210, they're considered really high performing. So that's a letter A. If it's above 800 kilograms of CO2 per meter squared, that's considered fairly high. So this just kind of gives you a sense, a range of emissions so you get an order of magnitude sense of scale. And so you need to combine these pictures, right? So for example, if you're, this is a hypothetical picture, but for example, if your embodied carbon is like 400 upfront, and then you annually you have a certain amount of emissions. One thing that oftentimes doesn't get factored in is we tend to assume that the operational carbon emissions is going to be the same the first year as like year 60 in the building lifespan. But for example, if we take seriously that we're going to reduce the carbon intensity of our electricity grids, like there's some proposals in the US for, getting to zero emissions by 2035, or maybe different states or different regions have their own, plans for the electricity sector. As that goes down, then the electrified buildings will also be quite decreasing over time as well. So that's just a sidebar point. But, the operational carbon emissions can vary a lot. There's a difference between standard performance buildings versus really high performing buildings, which can be much lower. And just to reiterate the point, I mean, this is kind of the extreme example. I'm sure in Nashville, the picture is going to look quite different. I would imagine the operational carbon intensity is much higher. But for example, I mentioned earlier, in BC, if we get electrified buildings down to 1.1, like 1 kilogram of CO2 per meter squared, the embodied carbon, this is just for a 5-story office building that I'm currently working on, is like 558 kilograms of CO2 per meter squared. If even over 60 years of analysis, 90% of the total carbon of the building is associated with embodied carbon. But obviously, if you have much higher operational carbon emissions, let's compare it against like what's a typical office in Vancouver or in BC, then it's about 40% embodied carbon over 60 years. So that's just a range of results to show. So now I'm going to move over to policies and standards. All around the world, there are voluntary green building standards and also regulation coming into effect that address embodied carbon in some way. And so these logos just kind of highlight some of the different programs that address embodied carbon in some way. And this was done in 2018. There's been a lot of recent efforts that have taken place. So, and broadly speaking, I see policies typically operating at 2 scales that correspond to these dark blue lines. One is at the material or product level. So that's looking at environmental product declarations, which I'll get into a bit later. I actually see that a lot in the US. So for example, if you've heard of the Buy Clean California policy, I think there's similar proposals in Washington, or the Marin County Low Carbon Concrete Code. These are trying to develop regulation that's focusing specifically at the individual material level. And then we also have policies that are addressing it at a whole building level. So not just at individual materials, but on a whole building basis, you know, if you compare it to a baseline, what percentage reduction in embodied carbon can you achieve? So for example, LEED with the USGBC, under the material resource credit, you can get up to 5 points for reducing embodied carbon. The CaGBC also has a zero carbon building standard. That's the Canadian Green Building Council. The International Living Futures Institute with their Living Building Challenge, and also through their zero carbon certification, they also have some requirements for reductions. And in Vancouver, we have probably some of the most ambitious policy efforts taking place. I'll get into that too as well. So I mentioned environmental product declarations. If you're not familiar with what that is, that's essentially like a food nutrition label, but for building products. So similar to nutrition labels, you know, they tell us what's the health impacts or the health content, per serving size of the food. Similarly, with a product EPD, in this case, concrete, we can say per meter cubed of concrete, what is the global warming potential or the acidification potential or all these impacts. So it gives us a sense of the environmental impacts associated with individual products. Now, essentially, these are life cycle assessments done on individual products. So for that manufacturer, for this particular brand of insulation, we're going to go through the whole supply chain, do a life cycle assessment, and quantify what those emissions are. And there's a third-party verified process to develop these environmental product declarations. They follow ISO standards. They avoid greenwashing, because oftentimes you hear a lot of claims made, a lot of marketing claims by different manufacturers, but EPDs actually allow for a better basis for actually understanding how the relative environmental performance compares between different products. And these EPDs can be at the industry average level. So for example, there can be a US or a North American average for wood or for concrete for different mixes, or they could be at the manufacturer or plant or product specific level. So, you know, this brand of a particular insulation from a certain manufacturer, we can get it down to that level as well. Okay, let me just check on time. I'm just gonna take a sip of water. All right. So some of the policies I mentioned, well, before I get into the policies, so LEED has, I mentioned, can get up to 5 points through the life cycle impact reduction credit under the material resource section, credit 1. So you get 1 LEED point just for doing a whole building life cycle assessment and just disclosing the results. So that's an easy LEED point. Next up, you can get 2 points for a 5% reduction, 3 points for a 10% reduction, 4 points for a 20% reduction, and some reuse requirements. And in certain regions, that may also unlock a regional priority point. So you can get up to 5 points. So if your project's going for, you know, LEED Gold or whatnot, has some LEED target, this can be a big part of your LEED strategy. And that's only looking at the life cycle assessments. There are some others associated with environmental product declarations as well. CaGBC, I mean, this is a Canadian standard, so maybe I won't get into that. And then the International Living Futures Institute, I mentioned, you know, if you're going for their zero carbon certification, they require 10% reduction in embodied carbon and also offsetting of the emissions. And they actually set a maximum cap for embodied carbon at 500 kilograms of CO2 per meter squared. The Living Building Challenge has a 20% reduction requirement. And now I'll get into the city of Vancouver. And, you know, especially for those of you that are interested in pushing policy, you know, locally, which I think is probably one of the most important efforts to really accelerate adoption of, you know, or having firms actually address embodied carbon on projects. I think regulation is the most impactful way you can do it. In Vancouver, back in 2017, under the green building policy for rezonings. So rezoning accounts for maybe half of the new construction in the city. So they have some requirements that you need to meet, including just doing a whole building LCA at the rezoning stage, and then updating it during building permit, and then finally at occupancy. So just by requiring all the firms to do an LCA at that stage, at that early design stage, helped build up a lot of the local industry capacity to, look at these emissions, to start thinking about them without having a specific requirement for reduction. Now they've just recently they passed the Climate Emergency Action Plan after we declared a climate emergency as a city. And the big target is by 2030, the embodied emissions in new buildings and construction projects need to be reduced by 40% compared to a 2018 baseline. So in the next decade, we need to get to 40% reduction. And this isn't just a voluntary requirement. This is going to apply to all new construction. So it definitely has gotten a lot of the local architects, structural engineers, all the industry players' attention. And so we see that regulation has really kind of accelerated focus on this topic. And actually our rezoning policy is going to be updated later this year to require at least a 10% reduction in embodied carbon. So I highly encourage any cities that are thinking about this to follow this type of format where you actually look at, can you first require design teams to do the LCAs so that they get familiar with the process, and then progressively step in reductions at the building level. Okay, so that's policies. Now we'll get into software tools. There's a tool called the Athena Impact Estimator for buildings. This is a free software tool. You can download Windows application. And it's quite easy to use. So essentially you can just do takeoffs from your drawings and kind of build up these assemblies through this program. So for your floor, you can build up the assemblies, what materials are in there, etc. And yeah, so it's good in that way. It's especially useful in the early design phase when you don't have a lot of detailed, quantity takeoffs and whatnot. You can kind of make assumptions for as you build up assemblies. However, it doesn't have a Revit integration. And so for larger, more complex projects, it can be more difficult to kind of keep your LCA model updated and accurately modeling all the materials that are going into your building. Next up, there's Tally. So Tally is a paid tool. I think it's like $700 US per year or something like that. So this is a Revit plugin, and it only exists as a Revit plugin. So obviously, it's great that it works within Revit, so you can map, all the materials that you've defined inside of your Revit model to their database of materials, and yeah, you can do your analysis that way, and it's quite good, especially for more detailed, complex projects. However, because it's purely a Revit model, only a Revit only tool, it can be challenging to maybe do design comparisons, or even in the earlier stages, if you don't have a Revit model, then you can't do an LCA. If you want to model different wall assemblies, you'd actually have to model it in Revit, like any different alternative assemblies, before you can map it to the database. So it can be a bit more challenging to compare different options, but it's a great tool. And then finally, there's One-Click LCA. It's probably the most expensive of the tools. There's different tiers of license, but like I pay for the expert license, it's like 3,000 US per year. This tool has a much bigger database of background data, environmental product declarations, and it works with Revit. It works with a lot of different design software. So there's integrations for a lot of tools, and it can be used in early design, also in late stage design. Yeah. So I actually did a comparison for the National Research Council in Canada on these 3 different tools. So I kind of, I won't get into the specifics in this presentation, but I can send out the slides afterwards, by the way. And so there's links at the bottom of all the slides with references. So you can kind of explore this a bit further later if you want to see how these tools compare. This is just based on my own assessment. But I will get into some of the data points. So if both Athena and Tally mostly use industry average data. However, they draw on different types of databases. Actually, all 3 of them draw on different databases. So one key point is that when you're doing an analysis, you want to stick to the same software throughout the design process so that your results are consistent and the background data and assumptions are consistent. Yeah, but both these tools mostly have industry average data, so they don't have as much, for example, manufacturer specific data, whereas One-Click LCA has a bit of both as well. So they have manufacturer specific data. Yeah. Also, you may have heard of EC3, which is short for the Embodied Carbon Construction Calculator. You can access it through the buildingtransparency.org website. So this is an open source database of all the EPD or many EPDs that are public. And so this is not a whole building LCA tool in and of itself. For one thing, it only looks at global warming potential. It doesn't look at the other impact categories. But the use of this tool is that it's more for during the kind of the tendering phase in a way. So let's say you've already kind of selected, you know, you're going with a concrete building, for example, and you want to compare between different concrete mixes between different suppliers. This is where you can kind of do that type of comparison, get a sense of the range of emissions within each material category, and go from there. And so the point of doing a life cycle assessment is to figure out where are the hotspots, where are the, you know, the aspects of your building that that generate the most emissions, and is there a way to reduce those emissions? So for example, this shows you this is just an example project that we did for an office where you can see the breakdown in emissions between the floors, the exterior walls, the foundations, interior walls, etc. And then also breakdown across different materials. So how much of that, the total emissions are associated with the rebar or the structural steel or the ready mix. Yeah, this is just mentioning it. So I think using Revit models is definitely really helpful. However, it has its own challenges sometimes. Sometimes there's information that's missing in the Revit model, or you gotta like clean up the Revit model. So it can be more accurate, but there's a lot of quirks to sometimes work out on that front to make sure that you're actually getting the right quantity estimates. Yeah. Oh. All right. Now design strategies for reducing embodied carbon. First off, before we get into design strategies, this is a great resource for looking at how to integrate embodied carbon considerations throughout the design process, from early schematic design to design development, all the way to construction documents, bidding, construction, right? So you can click on this link, you can see the bigger version of this chart, but yeah, I highly recommend you look at that so that you get a sense of like, what are the type of design decisions that you make at each phase. And yeah. Thornton Tomasetti has done a study of, I think, over 600 buildings internally. And so they looked at only the structural frame options. So not looking at, I don't think it includes like envelope or some of the other scopes of materials in a building. However, just looking at the structural frame of the building, they compared, you know, between, for example, concrete, timber, steel, hybrid, et cetera. And these are averages, I think, for what they found. So generally, timber or mass timber buildings or wood frame buildings, they tend to be lower emissions. Concrete buildings tend to be higher. However, there's big variability there too. So like what you do with the concrete mixes, what type of steel you use, that can change your results quite a bit. So you definitely need to do the analysis, but this is just to kind of give you a high level overview. So as I mentioned, we're going to go through all these key materials, starting with concrete. So concrete, the thing you want to pay attention to is the cement. So cement makes up about 10 to 12% of the concrete mix. However, it makes up 80 to 90% of the actual emissions associated with the concrete. So essentially anything that you can do to reduce the amount of cement content in your building can have a huge impact on the overall embodied carbon of your concrete mix. So what are some of those strategies? You can use Portland limestone cement, also known as GUL or general use limestone. So this is in contrast to regular Portland cement. So the difference is that you're basically adding a bit more limestone into your concrete mix and reducing the cement content. And so that's kind of low-hanging fruit. I don't know if this is standard practice in Nashville, but definitely ask your suppliers for this. That can lead to about a 10% reduction just on the concrete mix level. And then from there, you can also increase supplementary cementatious materials. So things like fly ash or slag. Again, those things will help generally correlate with reducing the cement content in the concrete mix. And so these are just based on my own estimates, but roughly, like just from some of the numbers that I've seen, roughly every 10% increase in the SCM content leads to about a 7% reduction in embodied carbon of the concrete mix. Again, these are high level numbers, but the key point here is that you want to optimize it by building element. You know, as you have higher SCM content, it can affect your curing times. And so that's just one of the considerations. So, you know, for example, your foundation, you may be able to go much higher on the fly ash or slag content versus your above grade floor slabs. So for each element of the building that uses concrete, you want to really optimize that and work with your structural engineer, work with your ready mix supplier on that. Also, if you can use performance-based specifications and avoid prescriptive requirements. So sometimes we see prescriptive requirements like this is the minimum cement content that we need, or the maximum water to cement ratio, or the maximum SCM content. Those are the types of things that can limit what a ready mix supplier can do in order to reduce emissions of the concrete mixes that they deliver. So rather, you want to kind of have performance-based metrics like strength, durability, cure time, et cetera, and let them kind of figure out the optimal mix. You can, well, actually, I won't get into some of these other factors, but those are kind of key strategies for concrete. Just to give you a sense of like how much reductions you can do for concrete. This is a Canadian example. So we're looking at the Canadian Ready Mix Concrete Association's industry average EPD. And if you look at just 35 MPa concrete, comparing it to the benchmark mix, so that kind of the average mix, if you use Portland limestone cement, that's the GUL, and you can get up to 35% or higher SCM content, you can bring it down to about 35–40% reduction. And I've also seen some of the manufacturer-specific EPDs lately that go much further than that as well. So a lot of reductions can take place on a per meter cubed of concrete level. So really focus on the concrete mixes. Next up is steel. So there's two broad ways of making steel. One is basic oxygen furnace, and then the other is electric arc furnace. Generally speaking, electric arc furnace steel is much lower emissions, about half, maybe even down to a fifth, depending on how it's produced. Basic oxygen furnace is how we make most of the steel in the world. So about 70% of the global steel production, is made using basic oxygen furnace, and it uses much less recycled content. It's mostly actually virgin iron ore, but it can be 25%, maybe much less. Whereas electric arc furnace is mostly recycled scrap steel, for example. So up to typically 97%, or yeah, very high recycled content. And because it's an electricity-driven process, electric arc furnace, if you think back to the electricity grid mix point that I made earlier, it matters where the steel is produced. So if it's produced in a state that has very low carbon grid electricity, that will affect the embodied carbon of the steel as well. So generally speaking, trying to specify steel that uses more electric arc furnace where possible. Although I will say that that's not a solution at the global scale, because we actually don't have enough recycled steel to satisfy global demand. So we still need to make primary steel through basic oxygen furnace, and that's we need to figure out ways of decarbonizing that as well. But yes, broadly speaking, it's important to think through like where you source the steel, what the emissions of those steel is, and also like how do you reduce the steel quantities on your project. Some of these points that I'm bringing up, that I'm talking a lot about material substitutions or how different materials or different manufacturers compare, but there's also a lot to be said around how do you actually use less materials. So work with your structural engineers on what's the optimal column grid spacing or whatnot. There's a lot of strategies that they can do to help reduce the material quantities used on projects as well. Then next up is wood. As I mentioned, generally wood is like quite low embodied carbon when we do our LCA studies. One thing I do want to highlight is that when you're looking at these case studies that, for example, compare wood building versus a concrete building, and they'll say it's a certain percentage reduction. One thing to keep in mind is, or a question to ask is, what is the assumption around biogenic carbon? How are they handling biogenic carbon? So for wood, and other biomass-based materials, there's a question of how biogenic carbon is modeled. So for example, sometimes people make the assumption that, hey, this log of wood or whatever, this wood stud or the CLT panel, there's this much carbon content stored in this piece of wood. And so they estimate what the carbon content is, translate that into CO2, and they multiply it by -1 and say, hey, this is actually stored. So this is negative, we're going to give some negative credit for storage. That can obviously change your results quite a bit compared to the conservative assumption to not include storage benefits as well. And then furthermore, there's a whole series of questions on like how how do we account for example, forestry related emissions, which aren't included in our EPDs for wood? Like what happens to the soil carbon? What happens when you cut down the tree? Like what if the tree were to keep growing? Like, do you account for that? Like the relative carbon differences there. What about the timing aspects around when the carbon sequestration and when the emissions are taking place? So because we're talking about forests, which have a lot of complexities, a lot of variability between different regions, different species, it's a living organism or living, ecosystem that's growing. So it can be very challenging to model all those aspects and to understand it. So that's definitely a big area of like current discussion, even amongst the experts. So, but yes, it matters you definitely want to source your wood sustainably. So look at sustainably sourced certified wood, especially FSC wood. They tend to, a lot of people think that they have a higher standards, or they may be more lower carbon. Okay, next up, aluminum. So aluminum requires a lot of energy. It uses almost 10 times as much electricity than steel to produce. So it definitely really matters where this aluminum is produced and that it uses a low carbon electricity mix. So interestingly enough, in Canada, we're the 4th largest aluminum producer in the world, and I think we're the lowest carbon producer because we have a lot of clean electricity. Most of our aluminum is produced in British Columbia and in Ontario, which have a lot of hydroelectricity. Also, we use the latest generation of production technology, so it's more efficient, and so that can influence things quite a bit. Aluminum is highly recycled, but it's important to note that similar to steel, we don't have enough recycled aluminum to satisfy global demand. And so it still really matters how we make the aluminum. Obviously, recycled aluminum uses much less energy and is much lower emissions, but as I said, there's not enough recycled aluminum. But on a whole building basis, generally speaking, aluminum is one of the highest impact materials. So you really want to use it sparingly and use it with reuse in mind. Yeah, I'll actually get into this point next. Talking about glass. So glass, there's obviously a lot of glass that's used in our buildings. It has decent impact. It's not a particularly high impact material, but due to the quantities that we use, it still kind of adds up. But I think the key thing to really look at is the framing options. So for your window frames, what are you using? Because that can actually really affect the overall embodied carbon of your facade. A wood frame window is much lower embodied carbon than an aluminum frame window. And if you look at curtain wall assemblies with aluminum mullions, it's the aluminum that's actually really driving up the emissions of those curtain wall assemblies. So that's something to kind of keep in mind. However, whenever you're talking about anything that affects the envelope of a building or that affects essentially the operational carbon emission considerations, you need to weigh the benefits and you don't want to just optimize for embodied carbon. So for example, if you look at double pane windows versus triple pane windows, well, obviously adding another pane of glass is going to be higher impact from the embodied standpoint, but maybe it leads to a lot more reductions on the operational side. So I'm definitely an advocate of looking across the whole picture and seeing what makes sense. One thing I will want to highlight is, so the same thing applies to insulation, adding more insulation, more material, more embodied carbon. There is definitely big variations between different types of insulation. So I've tried to kind of map this out. And so here I've looked at mostly industry average EPDs, but sometimes manufacturer specific ones where I don't see industry average data. So the top part is mostly XPS, extruded polystyrene, and spray foam insulation. And then I also have EPS, expanded polystyrene. Let's see what else is there. Polyiso insulation, mineral wool, fiberglass, and cellulose. So what I've mapped here is a kilogram of CO2 per meter squared of insulation at various different R values from R5 to R60. So for example, for XPS, it's roughly R5 per inch. So this is 1 inch of XPS. This is 12 inches of XPS. And you can see there's big discrepancies, especially for XPS and for spray foam. These numbers get really, really high. These are almost on a whole building level, almost the scale of whole building emissions, if you recall what I showed you earlier, kilogram of CO2 per meter squared, right? If you get, depending on the compressive strength at the highest level, 100 PSI, at 12 inches, which I know is a lot, that's 1,000 kilograms of CO2 per meter squared, which is really significant. That's more than most buildings, right? Even at the higher end. So the key takeaway here is, first off, many of the whole building LCA software tools, that, including the 3 that I mentioned earlier, significantly underestimated these emissions by an order of like 10x to 25x. So this did not show up in many of our LCA studies because they significantly underestimate these emissions. That is mainly due to blowing agents. So hydrofluorocarbons are essentially like refrigerants. They are thousands of times more impactful than CO2. So even small releases of these gas can have a huge global warming impact. And this was not fully captured in our software tools. And so that's why these impacts are so high. That said, different states, so Canada, as of January 1st, 2021, of this year, we have new regulation. So we banned the use of these HFC blowing agents in the XPS and spray foam. And as a result, many of the manufacturers had to make big changes to their supply chain, and they now have new products on market for that. Some states have also developed some of their own state level regulation on HFCs, but not all of them. So you can see all the gray ones are the ones that actually have that regulation. All the blue ones don't. So many of the states in the US don't have this. And so this is something to really keep in mind. If you're specifying XPS or spray foam, look at the blowing agent and mandate that you don't use HFC blowing agents, or that they need to use some sort of lower global warming potential blowing agent, such as HFOs, which is hydrofluoroolefins, instead of HFCs, which are hydrofluorocarbons. HFCs are the higher variety. The reason why I kind of started looking at a lot of this stuff was due to a book called Drawdown, which looked at what were the top solutions for global warming. And what surprised me and a lot of people was the #1 solution that, in terms of mitigation potential on a global basis, was refrigerant management. So higher than things that you would normally think, like, for example, wind turbines or solar, or even like plant-based diets. On a global basis, looking at how we address refrigerants was the top solution in terms of how much emissions reduction we can achieve there. And if you compare that to, for example, cement, which is something that we talk a lot about in the embodied carbon world, much lower mitigation potential. It's number 36 on the list compared to the refrigerant management one. So that made me think, I'm like, how come we don't actually hear that much talk about it in the building sector? I think now we're starting to hear a bit more, but like a couple of years ago, not really at all. This is getting a little bit technical, but just something to keep in mind. So I mentioned earlier, if you hear about kilogram of CO2 equivalent, that little E at the end of the CO2, what that means is we actually have many different greenhouse gases that affect the climate in different ways. So for example, CO2 is the main one people talk about, but then for example, methane is also very significant, but it has a different profile. It stays in the atmosphere for a different period of time. So you can see this is over 1,000 years. CO2, even after 100 years, 44% of the CO2 is still in the atmosphere. After 1,000 years, a quarter of the CO2 is still in the atmosphere. So it's still impacting climate change. Whereas for methane, it has something like a half-life of 12 years. So it has a big pulse of impact up front, but it decays very quickly. Now, when we're looking at these global warming numbers, we actually have to look at it over a time horizon. And this is unstated. Most people don't know this, but almost all CO2 emission statistics that you see, whether it's at the national level, at the IPCC level, all the way into like our LCA studies or our EPDs, they're all assuming a 100-year time horizon. And so you may have heard that methane is 25 or 28 times more impactful than CO2. That's over a 100-year time horizon. But in a 20-year time horizon, it's actually 3 times higher. It's like 84 times more impactful. This is true not just for methane, but also for refrigerants. So many of these refrigerants have very short atmospheric lifespans, like under 20 years. So you could argue that maybe a 20-year time horizon is more appropriate to look at, or it's just a different lens to look at it. In which cases, those refrigerants are 2 to 3 times higher impact than anything that you see published as well, because it's the time horizon assumption. So these are very significant from a climate change perspective. And I mentioned, R134A, that was the blowing agent that was commonly used in a lot of XPS insulation, for example. So very high impact, 1,400 times more impactful than CO2 in a 100-year time horizon versus 3,800 times more impactful. So refrigerants are a big deal. It's used in our insulation as blowing agents, and obviously in our mechanical systems, which is where it's mostly used. So this is also in the operational carbon domain. We tend to look at the operational carbon savings from using refrigerant systems. For example, using variable refrigerant flow. A lot of refrigerant charge in that system, but we don't account for leaks. We actually oftentimes don't even measure the leaks, or we have no idea how much leakage takes place. But if it does leak, it can actually be quite significant in terms of the emissions. So in this case, this was just an example for a 1-ton heat pump in New York. If you assume like 1% annual leakage per year, this is like 5.9 kilograms of CO2 per meter squared. But if you assume like 100% leak of the system, it's 58 kilograms of CO2 per meter squared. Now, in reality, it's hard to kind of estimate what the annual leakage rate is. That's more of an averaged assumption. Oftentimes when a system leaks, all the refrigerant leaks, right? So then the question is, how many times does it leak? If it does at all, how many times does it leak over the lifespan of a building where you need to recharge the system? So this can add up very quickly. So that's something that oftentimes doesn't get addressed. Also, in our LCA studies, we typically just look at the structure and the envelope right now. Those are kind of the main categories that we look at. But we oftentimes we don't quantify the embodied carbon associated with the mechanical, electrical, and plumbing systems. So think of all the ductwork, all the pipes, all the plumbing, all the air handling units, et cetera. The materials that go into it, all the steel, the copper, et cetera, we don't quantify that. And so there's different ranges of estimates. In this case, it's from the Carbon Leadership Forum, they did a study. They estimated between 40 to 75 kilograms of CO2 per meter squared. I've seen some studies from Integral Group that have gone up to like 2 to 300 kilograms of CO2 per meter squared, depending on the facility. So it can get quite high. Same thing with tenant improvements as well. So we're talking about interiors, finishes, furniture, cubicles. Those things oftentimes don't get addressed too, and they can be quite high. But the thing to keep in mind about these factors is these are the one-time emissions, but they actually get replaced at a certain cadence, right? So they have a certain service lifespan. So this is a simplified example, but let's say, for example, in a medium estimate, the structure and envelope is 400 kilograms of CO2 per meter squared. So that's like kind of the gray. And then we assume that the MEP system and the tenant improvements happen every 15 years. Those can add up to a point where that actually even eclipses the initial embodied carbon that we quantify using our LCAs, just of the structure and the envelope. So all that to say, we need to think about the lifespan of these things as well in this. And just to wrap up, another metric to think through is not just about material substitutions or how to use materials more efficiently. It's also worth considering, what if we actually look not just at kilogram of CO2 equivalent per meter squared of floor area, but rather we look per occupant. We see that floor area per capita is actually increasing in almost all regions. So you can see, so in the US, I think it's averaging about 700 square feet per person. So it's quite high, highest in the world. So can you make more efficient use of space? So so for the architects out there, like that's something to keep in mind, is it's not just about material substitutions. Can you make better use of the space, more efficient use of the space? And then also household sizes are decreasing across the world as well. Broadly speaking, I really advocate for looking for the blind spots. So embodied carbon, I mentioned, is a blind spot, or I refer to it as a blind spot. It's something that was ignored. It's a big problem. It's solvable. But also within embodied carbon, there's many blind spots, like the HFC blowing agents and insulation, refrigerant leaks, MEP systems, interiors, forestry impacts, growth in floor area. These are all blind spots. So I encourage you to kind of like seek that out for yourself as well. Finally, I mean, this is the first event for CLF Nashville, so it's great to see, those events taking place and all of you joining for this. There's many local hubs around the world that are starting up. You can join the online discussions as well. So this is, if you're new to the CLF community, you can join the Carbon Leadership Forum network. And there's a big kind of active online forum where there's many discussions around embodied carbon if you want to kind of stay up to date on the latest on that front. You can connect with me on LinkedIn because I share a lot of interesting information on embodied carbon if you want to stay connected on that front. And yeah, we do, my firm Priopta, we focus on whole building life cycle assessments. So if you need this type of analysis on individual projects, we're happy to help. Sometimes we take on research projects or inform policy making efforts as well on this front. So thank you very much. And now we'll open up for Q&A. Sorry, I think I probably take up most of the time. Was this scheduled for 1 hour or an hour 15?
An hour, but
Okay.
if anyone has any questions and you have a minute, we can
Right.
touch on them. I don't think anyone put any questions in the chat, but. And also just as a note in the chat, I just posted the link to the CLF Nashville page, and you can also join that, and Katie and I post updates for our local events there as well. And thank you, Anthony, for the great overview.
Yeah, no problem. I can stick around a bit longer too, but if you need to leave, you're welcome to. It seems like Shiva has her hand up.
Hi, Anthony. Thank you so much for your great presentation. It was really informative and engaging. I have a question regarding the slide that you mentioned, the gram of CO2 per kilowatt hour of electricity.
Yes.
Used in each city. So could you show that slide again?
Yep. Let's see. Okay, let me just scroll through. That was at the state level, but yes, I can.
Oh, that's a state level.
Yeah.
Oh, I see. So here I'm seeing biomass. Would you please let me know what is this biomass? It's biofuel.
Yeah. I'm not entirely sure like what form of biomass gets used in each state, but I mean, it could be like burning wood or I'm not sure, like wood chips or something, but I'm not sure what are the specifics for this. This was just kind of what was in the data set from the EPA.
Oh, true. So are we gonna have these PowerPoint? So I can use the link too.
Yeah, for sure.
EPA. Yeah, thank you so much.
Yeah. And Deva, do you want to unmute and maybe ask your question? Or maybe I'll just ask it. Okay, so it says, you mentioned should then embodied carbon and operational carbon analysis should be done side by side for more informed decisions. Yes, I do think that's definitely, that would be beneficial. I think right now they're a bit siloed because like it's just different area of expertise in a way. But I think there definitely needs to be communication between the people doing the LCA modeling and the people doing the energy modeling to kind of evaluate these different design strategies. Particularly because I think the relative balance between operational and embodied carbon can vary so much, like city to city, region to region, because of some of those factors that I mentioned earlier. So the trade-offs are going to be very different. Like I showed you earlier, BC, we're probably like the extreme example of like very low operational carbon. And so the trade-off considerations are very different for us versus, in another city or region. But yeah, great question. I think it's definitely much needed. Anyone else?
Also, one more question. Thank you for answering the previous one. There aren't any current carbon emission taxes right now in the States, right? I mean, there are certain policies and process specifically, I guess, in Washington area, DC area, but specifically in some of the states, there aren't any such kind of things. I mean, policies or in terms of penalties and fines for carbon emissions.
I'm not as familiar, but I know, for example, New York, they have their local law 97. So that's a very significant thing. They're putting a really high price on like even on existing buildings on the operational carbon emissions. I think it was like $200 something per ton. Like if you go over a certain period, so like they're changing the whole economics around like incentivizing retrofits and higher performance buildings. So I would say that's definitely coming. And so carbon taxes can happen in different ways. Now, specifically to embodied carbon, it may not directly affect it quite the same way. Like I could imagine it actually, oftentimes carbon taxes come more on the energy side or the fuel side of things. And so, for example, the fuel that gets used into the cement plant, maybe they pay the tax, but it may not kind of make it trickle its way all the way down to the building scale, where you kind of tax it at that level based on the LCA study. but that could be an interesting way of it going forward. But yeah, I'm not aware of what the rest of the situation in the US or what's available, what the carbon tax situation looks like.
Oh, thank you.
Mm-hmm. Anyone else? All right. Great.
Okay, awesome. Thanks again, Anthony. And then I also just want to let everyone know for future CLF Nashville events, we are having the first part of a concrete series on June 30th. So it's in exactly 2 months. And we're teaming up with
You cut out.
Oh, we lost you, Nicole. We're teaming up with Tennessee Concrete Association and Middle Tennessee State University.
Tennessee Concrete Association and I don't know if you can hear me. It says my internet is unstable. But yeah, so that's on June 30th if you'd like to attend that as well. And we'll send out event invites, and then also that will be on, information will be on our LinkedIn page if you want to connect there.
Great.
Thank you so much, Anthony. This was great.
No problem. Thank you. Thanks, everyone.
Everybody.
Thank you.
Thank you. Bye.
Thank you. Bye-bye.